shining, grass is green.
Hey, so the bell's not working. Can you make sure I don't miss lunch?
I will make sure you don't miss lunch. I promise.
Okay.
Okay.
Can I go to the bathroom?
Bring this again. Let's go. All right. So for today, and for the next week or so, we're going to look at the next section, 8.2, which deals with the other four trig functions. Now, some positives to focus upon. First, they will always appear in a similar form to what the sine and the cosine fit into. A tangent of bx minus c plus d is the one we're going to talk about today, the tangent function. And the way a, b, c, and d act is the same for tangents. So how b changes the period, it'll change the period for the tangent functions as it did for sine and cosine. How a changes the amplitude, how far it goes up and down, it'll do the same thing for tangent. The only difference is tangent looks different from the other two. So to start with, I'm going to pull up Desmos to show you what the tangent function looks like and point out a couple of simple things. Here we go. Who is calling me during the day? I hate you. Sorry. I get like 5 phone calls a day now.
Calling you about your giggles in the workie.
I get phone calls that are like, we'd like to consolidate your student loan debt. And I'm like, no, you don't.
Yeah, I get those too.
You don't even.
Exactly. Yeah.
Fine. Okay. So first of all, here's the tangent function. In all of its beautiful, beautiful glory. Just like sine and cosine, it is a cyclic function, meaning it repeats many, many, many times. The main difference is, well, obviously how it looks. You know, the sine function is a wave, and so is cosine. It just waves back and forth, oscillating between -1 and +1 on the y-axis. Tangent doesn't do that. Tangent has a slightly different form. And there are some unique, real-world examples of how tangent is designed to fit in. I will actually show you guys a couple of gifts tomorrow that I hope will better explain kind of why tangent looks the way it does. In the meantime, just like with sine and cosine, we're going to focus on one period. Now, this period we focused upon with sine and cosine started at the origin and went to the right. We cannot do that with tangent because tangent is actually centered on the origin. So we're going to focus upon is this period here in the middle. We're going to talk about this period's properties and how it fits together, and talk about the way we can learn to draw this graph of this period successfully, the same way we did it with sine and cosine, using these 4 values. Just like with sine and cosine. My goal will be to focus upon A and D changes first, then focus upon what happens when B and C change, which are the more complicated ones. We will likely spend 3 or 4 days just talking about tangent. Rizal, focus please. That being said, first thing I want to point out is when it comes to tangent, there are a few properties we need to know. So let's go to this on the board. For tangent, here we go. First thing to point out, tangent is the first function we've had in this class that uses asymptotes. Asymptotes from algebra are defined as spaces. A function approaches but does not cross. To illustrate this, I'm actually going to put the equations of the asymptotes into this picture so you can see them very nicely. And here they are. So you can see this middle portion here, this left-hand red line, the purple graph of tangent approaches that red line, but never quite gets to that red line. This is an asymptote. This is a left-handed asymptote because it approaches it to the left.
What does that say?
Oh, spaces, a function approaches but does not cross.
Okay.
A little nicer?
Yeah.
A little nicer?
Really fast. I'm gonna.
Better?
Yes.
Okay, I will try to make sure it's better. Now there are 2 different kinds. Yeah, sorry. My handwriting has never been that good. With this one, we're focusing on vertical asymptotes. These are, going up and down. And so, your vertical asymptotes are ones that bind it going up and down. So it binds the thing left to right, as weird as that sounds. The vertical asymptotes go up and down. It binds them left to right. So it has to be somewhere in between this function. Now, it turns out, as weird as it sounds, sine has an asymptote. Sort of. And it goes to 1, but never really crosses 1 except those very specific spots. So it sort of has what's called a horizontal asymptote, but this one has a firm asymptote, meaning this will never actually get to that red line. No matter how far you scroll down, never touches it. Gets close, never touches. So again, an asymptote, it's a space a function approaches but does not cross. In this case, we're dealing with vertical asymptotes. Now, specifically to tangent. Next one to talk about, there is, for tangent, a single big shift. That is true. Let's remind ourselves from yesterday, a couple days ago, sine and cosine. The equation for the period is 2 pi over b. For tangent, the equation for the period is actually just pi over b. This is because to complete one cycle, tangent only has to go a single pi unit, whereas sine and cosine had to go 2 pi units to complete one full cycle. The tangent repeats more often than both sine and cosine. Now, other than that, the other thing we're going to focus upon is a very specific table that, just like what we had with sine and cosine, about values that are specific and need to be recognized. This table, to illustrate this, consists of 5 places, just like they consisted with 5 places for sine and cosine. But this time, those 5, not quite as nice. So, the first space is where the left asymptote is going to be. We have to know where the left asymptote is going to be in order to graph this function. Secondly, we need to know where the right asymptote is going to be in order to graph this function successfully. It is helpful to know where the center of the function is going to be and where the 2 edges of the function are easiest to define. And these 2 are the easiest to define, by the way. Hey, come here. Thank you. These 2 values are the best ones to graph with. Everything else is a weird decimal, but these 2 are the only nice values that are easy to find. So, these 5 points will be how we define tangent for every single graph we're going to do. We're going to define it by the left and right asymptotes, the center, and again, 2 quarters, determining how everything fits together. Now, as we discussed in the last section, there are multiple ways to go about graphing these functions. You can graph them by adjusting them by A, B, C, and D in the picture. You can graph them by using a formula. Now, we already had a lot of formulas in the last section. If you want to, in a little bit, I will show you the tangent formulas. Long list. It's not exactly a nice list either. And that's just the tangent. We're also going to talk about cosecant, secant, and cotangent. The formulas, if you use them properly, are very nice. You plug numbers in, you will always find all 5 points in the asymptotes and get the answer. But in terms of doing it for the test, it's one of the hardest because there's so much to memorize. Take a look. I'll showcase this in 2 ways. The first way, this is the original tangent.
It's 11:19.
That's when we got up.
We got 11:17.
Mine says 11:18.
Mine says 11:17.
Then let's go to lunch. Alright, before we went to lunch, we talked about the basic properties. You have the idea of an asymptote here. The fact that it's vertical will dictate how we draw this thing. And that the period is based upon values of pi rather than values of 2 pi. So let's look at a basic tangent picture. And I want to point out how all these fit together. And you'll notice on the right-hand side, we have 5 points that dictate how to draw it. Same as we did with sine and cosine. Here we go. So, unlike with sine and cosine, I'm going to kind of go in a different order. Now, depending on how you go about it, you could actually use the same process, where you start by finding the outsides and kind of work your way in. It does work very nicely. But for tangent, for some reason when I was growing up, my teacher always taught me to work inside out for tangent. Again, I think it means memorizing more stuff, but that's just how I learned it. And so Maybe you'll do it my way. Maybe you'll stick to the same way you can do it with sine and cosine. Again, you'll eventually do all 5 of these pieces. What order you do them in is kind of up to you. So let's look at all 5 of them. So this time, I'm going to start in the center. The center is located at 0, 0, which is right here. At negative pi over 4, we are at negative 1. So I go to negative pi over 4 on the x-axis. I come down here to negative 1, and there's my dot. At pi over 4, we are at positive 1. So we go to pi over 4, I go to positive 1, which is right there. Get my 3 dots. If you're not careful, these look like a nice line. But it is not a line, it is tangent. And that's why it's important to remember the last piece, that these last 2 values are asymptotes. So I'm going to start by drawing the asymptotes, and then draw the line itself. The asymptotes here in green. At negative pi over 2, there will be an asymptote. So a nice vertical wall. And this function will approach, but not cross. Here at positive pi over 2, same thing. It will approach this line, but not cross that line. That's going to force this red graph to act in a very strange way. It will approach this line the farther we get down the graph, but never actually cross it. Over here, the same thing. It will approach, but never cross. In the middle, it almost, if you think back to algebra, looks kind of like a cubic. They are very similar. Just have slightly different functions, as you can see over here in the table. So again, notice to draw this, I focused upon the 3 middle values this time, and then put the boundaries around it, and then kind of stretch them to make them work. I will, throughout the next couple days, do it both ways. I'll do it more like sine, where we figure out the 2 boundaries and then put everything in the middle. And I'll do it like I was taught, where you do the middle first and work your way outwards. Both work very well. Now, this is the base sine, the OG tangent. If we have values for A, B, C, or D, all of these places can shift or move to adjust, making a new function. What I'm going to put on the board here in a second is a table. This table contains all of these points written as changes to A, B, C, or D. Let's take a look. Okay. This table, with the introduction of these variables, it gets a lot more complex, but what I want to focus upon is the parts that are the same. So let's focus this one at a time. In my original function, my D value is 0. So you can see quite clearly, since my D value is 0, that the middle value always has a value of D, because it's how much it moves up and down. The boundaries are defined by the phase shift as well as B affecting the period. And it happens on both ends, that they have very similar formulas in how they move. They're affected by the phase shift and either adding the period or subtracting it. The 2 inner values, similar, except instead of being pi's over 2's, they're pi's over 4's. But again, the phase shift affects each one of them. So we'll start off with primarily looking at ones where there's no phase shift. So most of these formulas have a lot simpler versions if there's no phase shift. You can basically erase every C over B if there's no phase shift, which makes these formulas a lot easier to manage, a lot easier to deal with. Just like with last week and last time, the phase shift is the tough part. If there's a phase shift, everything has to interact around that phase shift. So what we'll do is we'll spend a significant amount of time over the next couple of days looking at what happens when there's no phase shift between A, B, and D. Because if any of those change, these points can have very predictable results. It is only if there's a value of C that everything goes kind of crazy. And as a final reminder, everything in this formula, A, B, C, D, acts the same way it did with sine and cosine, but to these new 5 values, as opposed to cosine's 5 values, as opposed to sine's 5 values. So again, this table looks nasty. What I want to point out is, on the x side, everything is just being adjusted by the phase shift. So if you ignore the phase shift, all the formulas are a lot easier to deal with. On the right-hand side, 2 of these are asymptotes. The other two are based upon the amplitude and the midline. And so again, everything kind of fits very nicely together. In approximately 28 minutes remaining in class, on our graphical please. Now, as we did with sine and cosine, I'm going to start by looking at the very, very basics. If our functions have just an adjustment to A, or just an adjustment to B, or just an adjustment to C. As you can see, this table is pretty complex. So what I'm going to do is, as I go through this process, I'm going to focus on how do I do it if I don't want to memorize this table. How do I adjust it? How do I make it work without memorizing this big list of formulas? Because again, there are 6 trig functions. Do you want to memorize this table for all 6 of them? I don't want to memorize it for one of them. In fact, I don't have this table memorized for any of them. But to do that, you have to be willing to look at it and say, how is A, B, and C doing it, as opposed to just plugging to a formula and close. So it's a little different. Well, let's do this. I'm going to copy this table over to this board over here. And I'm also going to put with it like variations that we had from last week. Things like the phase shift being defined using C and B. All those little pieces from last week that we did with sine and cosine. Then we're going to attempt to graph a couple of equations where we make one change at a time. Let's do it. Our table first. All right. Now, for this table, I will put the entire table up here. But do note, for the first couple days, just like before, we will not be doing any phase shift problems, meaning there will be no C's anywhere in here. So here we go. The top one, C over B minus pi over 2B. Second one, C over B minus pi over 4B. Middle one, C over B. Next one, C over B plus pi over 4B. And the last one, C over B plus pi over 2B. Okay, now what happens up here? This first one is undefined, but I'm going to remind myself that this is an asymptote. Because I don't want to forget that it's not just undefined, it's an asymptote. That's not how you spell asymptote. Asymptote. Okay, this one is defined as D minus A. This is defined as D by itself. This is defined as D plus A. And this is defined as undefined another asymptote. All right. So our first example. Now, just like with last week, and that's why we do sine and cosine first, is because those two tend to follow much stricter rules, have less complexity to them, and so it's easier to talk about A, B, C, D in that context. Today, just like with last week, I'll begin by identifying which component we have and what it is. So, what's my A value? What's my B value? What's my C value? What's my D value? How will that affect my picture? And then we'll graph it. First example. Here we go. Now, unlike with sine and cosine, which we primarily focus to the right of the origin, tangent is nicely focused in the center. So I'll graph it a lot more like algebra did. All right, here's my equation. 3 tangent of x. Okay? Whew. Right. Someone say this graph is right. Because it's right. Makes you want to cry. All right. Let's do it. Graph this function. I, again, will think in mind of what the original table looks like. But what I'll do is I'll make changes to it based upon what this thing does. So, to do so, I'm going to ask the same question we asked last week. Where's the middle or midline of this going to be? What's the asymptote going to be? What is the phase shift going to be? What's the period going to be? Now, because this is tangent now, some of those have shifted. The midline is still based upon the d value, but now it's based upon where the center of the function is going to be, the same way it was for sine and cosine. The center in this case is just the center up and down and left and right. The amplitude is still the amplitude, but now it's going to be the point that we're crossing, that dot and dot, the two main dots to the sides. That's going to define my amplitude. And then we have my phase shift, which is still going to be how it moves left or right. My amplitude, that would be C over B. And then lastly, my period, but because this is tangent, the period has changed to being pi over B, not 2 pi over B. One last thing I make sure to put in, because it is A, the amplitude is absolutely valued. All right. Let's go through each of these as we go. And as we go through them, I'm going to make my adjustments. Here we go. First one. Look at midline. The origin, the x-axis. Since there is no value for d, I will not move my picture up or down. So remember, keep in mind, normally it is centered, up one, down one. Again, normally it is centered, up one, down one. The midline is on the x-axis. That tells me it's going to be on my midline. Okay? Next, asymptotes. See, this problem, what is my asymptote? Oh, shoot, I'm going out of order. Keep it the same, Douglas. I tried to switch it up last block, and it failed miserably. We're going to have to redo it tomorrow. Like they were wanting to cry. Let's try to keep it as much as possible the same as last week. So after I do the midline, my next step is amplitude. Same as last week, okay? Let's try amplitude. What is the amplitude for this problem? 3. Now, what this tells me is this is where those next two dots are going to go. So remember, the midline is in the center. The two dots represent my amplitude. So it is 3 above the midline and 3 below the midline. Okay. Next, I do my phase shift. All right, for this problem, what is my phase shift? 0. There is no value for C. There is no phase shift. All right, and the period. Just pi. Now, as I discussed, when I graph tangent, I like to work from the center to the outsides. And here's how you do it.
Wrestlers need to be released at this time. At this time, I need the wrestlers to please be released.
The first dot goes in the center, it goes on the midline, and it goes on the phase shift. So my first dot, here's the midline, there is no phase shift, so my first dot goes right there in the center. Next, I'm going to work outside. So I work the inside, now I work the outside. Where are my asymptotes? So remember, the period is pi. Half of that needs to go to the left, half of that needs to go to the right. So this is going to cause my amplitudes to be over here at negative pi over 2 and at positive pi over 2. Because again, the period is split half and half, one on each side. These red lines up here are my asymptotes. I can't write as, but asymptotes. Those were terrible lines, Douglas. They were terrible. Might be the worst lines I've ever done. That's not true. You've seen worse. Put them again. My asymptotes. They should be right here. Sort of.
Wait, so how do you know where those go?
Again, the phase shift tells you how far to go left and right. Since I didn't go left or right, the period is centered, unlike with sine and cosine. Sine and cosine starts in the origin and goes to the right, whereas tangent is centered on the origin. So half it has to go to the left, half it needs to go to the right. So notice I find the center first and then put half left and half right.
Okay.
Always the center first. So if my phase shift somehow put me like over here, half of it would need to be on this side of it, and half of it would need to be on that side of it. Because remember, we're defining where the center is, and then branching from the center from a few spots. This is what makes tangent different. Sine starts, finishes. Cosine starts, finishes. Tangent has a defined center and it asymptotes around it. So it's better to have a start with the center and branch out from there than to go the other way. Okay. Next piece. And again, I can also tell where those were plugging in the formula. Right? I plug in C over B. C is 0. B is 1. 0 divided by 1. Oh, sorry. There. C over B. So 0 divided by 1 would be 0 plus 2 pi over, sorry. Zero over 1 would be 0 plus pi over 2 times 1 would be pi over 2. So that's why it's pi over 2. That's plugging in here. 0 minus pi over 2 is why I get negative pi over 2.
Will always be 3D.
Say again?
Will I always be like 3D so if we have like 3 with 2 and 2 times 2 and this one?
Yeah.
Yeah.
Yep, always.
So, we're only gonna use 3 points.
Yep. 3 points plus the asymptotes. That's the key. It's 3 points plus the asymptotes. It's still 5 things for each trig function. It's just what those 5 are. In cosine and sine, there were 5 points. And now we're using 3 points and the asymptotes to get it instead. Here we go. Last piece. Where did the 2 points go? Now again, I could plug in the formula, but again, it's going to be halfway in between. Notice that for sine and cosine, everything was halfway in between something else. Halfway in between something else. Halfway in between something else. Well, halfway in between these two, I'm going to also have something cool happen. So halfway between negative pi over 2 and 0 is negative pi over 4. Halfway between positive pi over 0 is pi over 4. What happens? Well, these 2 points go on the amplitude. Which means for this one, the left-hand side goes down to the amplitude. The right-hand side goes up to the amplitude, giving me my 3 beautiful points that I then merge with the asymptote. Like that, and like that. Okay, I'm going to go back a couple steps and run through it again, because this one is tricky. So first, I'm going to go back a couple. I begin by defining where the center is using the phase shift. So we define the center using the phase shift on the midline. That's why the yellow dot is right there. Next, we define the 2 boundaries, the 2 asymptotes, using the period and the phase shift. So the period is pi, so an even amount is split to the left of the middle, an even amount is split to the right of the middle. That's how we define the middle. And then, in the middle of each of those, we place our remaining 2 points. So we have the 2 asymptotes, the center, point, and point. Total of 5. Those 2 points will go halfway in between, one of them on the bottom asymptote, Oh, sorry, not asymptote, amplitude. The other one on the top, amplitude. So for this problem, I want to point out the points that matter. So, little table of x's and y's. All right. At negative pi over 2, we have an asymptote. So it is undefined. At negative pi over 4, we are at negative 3. Because remember, it's on the amplitude, but it's down on the amplitude, so it's down 3. That's why it's at negative 3. The middle is at 0, 0. The bottom is at pi over 4, positive 3. And at pi over 2, we're back at the asymptote again. So, just like the sine and cosine, we will define all of these with 5 values. 2 of them are asymptotes. One is based on just the phase shift in the midline. The other is based on the phase shift in the period. With those 5 points, we can always generate a tangent function. And just to verify this is right, I will in a moment pull up Desmos and we'll graph this with the computer. And verify that these 5 things are happening. Now, it's a little harder with Desmos unless you do it right, so we'll showcase that too. But here we go. I'm about to change the screen. All right, my points are at negative pi over 2, I have an asymptote. Negative pi over 4, I'm at negative 3. 0, I'm at 0. At pi over 4, I'm at 3. Pi over 2, I'm back at an asymptote. Go to Desmos. My equation was 3 tangent of pi over 3. Okay. I guess that's interesting enough. Where are my asymptotes? Well, if I zoom out a little bit, you can clearly see there's going to be one right here and one right there on each side of it. I put my 2 in. Yep, it's clearly surrounding that purple line in the middle. It never goes past it on the left, never goes past it on the right. That looks pretty beautiful. Okay. Next, where are my points? Well, one of my points should be at positive pi over 4, comma 3. And one should be at negative pi over 4, comma negative 3. Throw my dots there. And there. What did I do? What did I do? Oh, I know what it is. I went to this one. So there they are. There are my 3 points. One there, and one there. Come on, come on. There we go. Left hand boundary, right hand boundary, center, right point left point. 5 things. Defines tangent. Do another. Again, we've just moved change A, we'll do one more change of A. See how it changes the function. Again, a lot of this will feel very similar to last week. We'll ask about things like the midline, the amplitude, the phase shift, and of course the period again. It's important to remember the differences between sines and cosines. If you put anything else to start today, I'd recommend part of that be what are the differences between the two, because there's a lot of similarities. One difference. Sine and cosine usually start at the origin. Tangent is centered on the origin. So when it moves, everything moves around the center at the origin, not around the other side. Look at the next one. All right. You notice that I put a lot of dashed lines up here? Some of them are things like amplitudes or midlines. Some are asymptotes. The ones that are asymptotes really, really matter because those I can't actually get to, I have to approach. Whereas midlines and amplitudes, I can touch those whenever I need to. Let's do it. Tangent of x with a negative 2 up front. Okay, just like before, I'm going to approach it by looking for those 5 values based upon A, B, C, and D. So the same pieces we had last time, amplitude and midline are typically in the first, phase shift and period typically come at the end. Here we go. Midline. What do we got for the midline for this problem? 0, so the x-axis. Amplitude. How far up or down are my first major points going to go? 2. Okay. Phase shift. There is none. And finally, the period. Again, I can plug into the formula there. My b value is 1, so pi divided by 1 would be just pi. Now I got all the pieces I need to get this thing started. All right, let's define the center first. Center. The center will always be on the midline on the phase shift. So I have the midline as the x-axis. I have that move left to right, so my center should be on the origin again. Again, I'm not moving up or down because there's no number on the outside being moving it up or down. Next, I'm going to put some stuff up here. I'm going to count for the first time. 1, 2, 3, 4, 1, 2, 3, 4. Okay. Amplitude. Amplitude is 2, which indicates that 2 above the midline and 2 below the midline is where our first next set of points is going to be. So we go up 2. There's my amplitude. Down 2. There's my amplitude. And just like last week, these are again based upon where the midline is. It's up 2 or down 2 from the midline. Next, I've got my center point. Let's get our 2 boundary asymptotes. Now, our 2 boundary asymptotes, it's centered on the origin. The period has to go an equal amount on the left and an equal amount on the right. That is why this period will be split by pi over 2 and negative pi over 2. Again, if there's no shifting, this is a common one. Now, the big difference between these two is the red lines here are amplitudes. We can cross an amplitude. We cannot cross an asymptote. We can approach it. We can get near it. We cannot cross it. I can't spell all today. I got asymptote and amptote. It's not Friday yet. I did it again. What? All right. Something. Okay. For our next dots. Next dots will occur halfway between again. So just like with sine and cosine, we go halfway between. Halfway between 0 and negative pi over 2 is the dot, negative pi over 4. Halfway between 0 and positive pi over 2 is the dot, positive pi over 4. Now, my dots take place on the amplitude, to the left to the right, on my midpoints. Now, because this is a negative 2, as a reminder, negative 2 always flips it upside down. So normally tangent starts low, hits the middle, goes high. Because it is negative, those are the opposite. It'll start high, hit the middle, go down low. Which means my amplitude is actually going to be right here. Halfway in between the two on the amplitude, but because it is negative, it is on the left upper and on the right bottom. Again, because of the negativity, it swaps those two. Once I've got my 3 dots and I've got my asymptotes, the last thing is make it look like tangent. Okay, remember tangent is asymptotic on one side, hits the center, and does the same on the other. So comes here, hits the asymptote, comes down, hits it again. No, I'm so close.
Yes.
There we go. There is our negative 2 tangent of x. So beautiful. So amazing. Shania Twain, sing songs about being like that. No? Dang, I feel like a Trig function. No? No? I thought it was really clever. Okay. As I said before, we're going to focus upon small changes to tangent. Go over those changes. Then we'll do the other 3 trig functions in time.